Last week we saw two simple sorting algorithms, selection sort and insertion sort. These were attractive because they corresponded to the manual way in which we would sort items by hand. On the other hand, we analyzed these to see that the worst case complexity is order n squared, where n is the length of the input list to be sorted. And unfortunately, n squared sorting algorithms are infeasible for n over about 5,000 because it will just take too long. And on the other hand, 5,000 is a rather small number when we are dealing with real data. So let's examine a different strategy altogether. So suppose we had the example where you were a teaching assistant and you were supposed to sort the answer papers for the instructor. Now, supposing the instructor had not one teaching assistant but two teaching assistants, and the job is distributed to the two teaching assistants. So each one is told to go with half the papers, sort them separately and come back. And then the instructor has to put these two lists together. So in other words, you divide the array initially, the unsorted array or list, into two parts. And then you hand over these two parts to two different people or two different programs if you want to sort. So you sort these two halves separately. And now the key is to be able to combine these two sorted things efficiently in a single sorted list. So let's focus on the last part. How do we combine two sorted lists into a single sorted list? Now this is again something that you do quite naturally. So supposing you have the two outputs from the two teaching assistants, then what you would do is you would examine, of course, the top paper in both. Now the top paper on the left hand side is the highest mark on the left hand side. The top paper on the right hand side is the highest mark on the right hand side. So the maximum among these two is the top overall. So you could take the maximum, say this one, and move it aside. Now you have the second highest on the right hand side and the highest on the left hand side. Again, you look at the bigger one and move that one here, and so on. So at each time you look at the current head or top of each of the lists and move the bigger one to the output. Right? And if you keep repeating this until all the elements are over, you will have merged them, preserving the sorted order overall. So let's examine how this would work in a simple example here. So we have two sorted lists, 32, 74, 89 and 21, 55, 64. So we start from the left and we examine these two elements initially and pick the smaller of the two because we are sorting in ascending order. So we pick the smaller of the two, that's 21, and now the second list has reduced to two elements. So at the next step, we will examine the first element in the first list and the second element in the second list because that's what's left. So among these two, 32 is smaller, so we will move 32. Now 55 is the smaller of the two at the head. Now 64 is the smaller of the two at the head. Notice we have reached a situation where the second list is empty. So since the second list is empty, we can just copy the first list as it is without having to compare anything because those are all the remaining elements that need to be merged. So having done this, now that we have a procedure to merge two sorted lists into a single sorted list, we can now clarify exactly what we mean by merging the things using merge sort. So merge sort is this algorithm which divides the list into two parts and then combines the sorted halves into a single part. So what we do is we first sort the left hand side. So we take the positions from 0 to n by 2 minus 1 where n is the length. So this is left and this is the right. Now one thing to note is in Python notation, we use the same subscript here and here because this takes us to the position n by 2 minus 1 and this will start at n by 2. Right? So we will not miss anything nor will we duplicate anything. So it's very convenient. So this is another reason why Python has this convention that the right hand side of a slice goes up to the slice minus 1. So if we write something like this, we don't have to worry about whether we have to do plus 1, minus 1. We can just duplicate the index of the right hand side and the left hand side and it will correctly span the entire list. So what we do is, this is a naturally recursive algorithm. We recursively use this algorithm to sort the first half and the second half, and then we merge these two sorted halves into the output. Right? So the important thing is we keep repeatedly doing the same thing. We keep halving, sort the half, sort the other half, and merge. And when do we reach a base case? Well, when we reach a list which has only one element or zero elements, there's nothing to sort. Right? So in such a situation, we can just return the list as it is and then rely on merging to go ahead. So once again, let's look at an illustrative example. supposing we have 8 items to sort which are organized like this. The first step says divide it into 2 and sort each separately. So we divide it into 2 groups. We have the left half and the right half. Now these are still things which you don't know how to sort directly. So again we divide it into 2. So the left half gets divided into 2 further subdivisions, and so does the right. Now we have lists of length 2. We could sort them by hand, but we say that we don't know how to sort anything except a list of length 1 or 0, so we further break it up. So now we have trivial lists 43 and 32 on the left, 22, 78 and so on. So we end up with 8 lists of length 1 which are automatically sorted. At this stage, the recursion comes back and says, okay, you have sorted the sublist 43, for example, for this list. We have sorted the left into 43 and the right into 32 in a trivial way. So we need to combine them by merging. So we merge 43 and 32 applying our merge procedure, and we get 32 before 43. When we merge 22 and 78, they remain in the same order. Here 57 comes before 63, and finally 13 comes before 91. So now at this level, we have 2 lists of length 2 which are sorted, and so they must be merged. And similarly here we have 2 lists of length 2 which are sorted, and they must be merged. So when we merge the first pair, we get 22 followed by 32 followed by 43 followed by 78. And similarly here we get 13 followed by 57 followed by 63 followed by 91. Right? So after doing these 2 merges, we have now 2 lists of length 4, each of which are sorted. And now we will end up picking from this 13, and then so this is 13, and then we'll pick 22, and then we'll pick 32, and then we'll pick 43, then 57, then 63, then 78, and then 91. Right? So this is how this recursion goes. You first keep breaking it up down till the base case, and then you keep combining backwards using the merge. This strategy that we have just outlined for merge sort is a general paradigm called divide and conquer. So if you have a problem where you can break the problem up into sub-problems which do not have any interference with each other. So here, for instance, sorting the first half of the list and sorting the second half of the list can be done independently. You can take the papers assigned by the instructor, give them to 2 separate teaching assistants, ask them to go to 2 separate rooms. They don't need to communicate with each other to finish sorting their halves. So in such a situation, you break up the problem into independent subproblems, and then you have an efficient way to combine the solved subproblems. So that is the key, that how efficiently you can combine the problems. If it takes you a very long time to combine the problems, then it's not going to help you at all. But if you can do it in a simple way, like this merge sort, where we do the merging by just scanning the 2 lists from beginning to end and assigning each one of them to the final thing as we see it, then you can actually derive a lot of benefit from divide and conquer. So let us look a little more in detail at the actual algorithmic aspect of how we are going to do this. So first, since we looked at merging as the basic procedure, how do we merge 2 sorted lists? So as a base case, if either of them is empty, as we saw in the example, we don't need to do anything, we just copy the other one. So we are taking 2 input lists A and B, which are both sorted, and we are trying to return a sorted list C. So if A is empty, we just copy B into C. If B is empty, we just copy A into C. Otherwise, what we do is, both are not empty, so we want to take the smaller one of the head of A and the head of B and move that to C, because that will be the smallest one overall in what is remaining. So we compare the first element of A and B, and we move the smaller one into C, and we keep repeating this until all the elements in A and B have been moved. So this is a Python implementation of this merge function. In general, the 2 lists need not be the same length. So we are merging A of length M and B of length N into an output list of length C. So initially we set up M and N because we need to keep track of how many elements we have moved in order to decide when to terminate. So we set up M and N to point to the lengths of A and B respectively, and we initialize the output list to be the empty list, because remember that in Python, the type of C will only be known after it's assigned a value. So we need to tell it that initially the output merge list is an empty list, so that we can then use append to keep adding items to it. Now what we are going to do is essentially start from the left hand side of both A and B. So we're going to start here and walk to the right. As we go along, we're going to move one of the two elements. So we need an index to point here. So we use the index I and j to point into A and B respectively. And initially these indices point to the starting element, which is 0. So as we move along, if we move I from 0 to 1, that means we have processed one element in A. If we move it to 3, we have processed 3 elements in A, and so on. So at any given time, I plus j will tell us how many elements have been moved so far to the output. Eventually, everything in A and everything in B must be moved to the output. So this will go on so long as I plus j is not reached the total m plus n, which was the total number of elements we had to move to begin with. So while I plus j is less than m plus n, we have to look at different cases. So the first two cases are where one of the two lists is empty. Either we have reached the end of A, so I has actually reached. So remember, the indices go from 0 to m minus 1 and 0 to 1 to n minus 1. So if I has actually gone to m, that means that we have exhausted the elements in A. So we append the next element in B and we keep going by incrementing the pointer in B or the index in B. Similarly, if we have reached the end of B, we append the next element A and we go back. Now remember that at this point, because I plus j is less than m plus n, if we have finished m elements but m plus n has not been reached, there must be some element in B. Similarly, if we have finished we have finished n elements in B, but I plus j is not yet m plus n, there must be at least one element left in A. So these two things will definitely work just by checking the fact that we haven't finished all the elements, but one of the lists is exhausted. Now, if neither list is exhausted, then we have to do a comparison. So we come to this case and we check whether the element in A is smaller than or equal to the element in B. So at this point, we are in general looking at some AI and some Bj. So we have to decide which of these two goes into C next. So the smaller of the two, if it comes from A, we append that to C and we increment the I pointer. Otherwise, we append the B value, increment the J pointer. So at the end of this loop, what we would have done is to have transferred m plus n elements in the correct order from A and B into C. So let's just verify that this code that we have described works in Python as we expect. So here is a file merge.py in which we have exactly the same code as we had on the slide. So you can check that the code is exactly the same. It goes through this loop while I plus j is less than n plus n, and it checks the 4 cases, and according to that copies either an element from A to C or B to C, and finally returns the list C. So the simplest way to do this is to try and construct two lists. So suppose we take a list of numbers, say the even numbers from 0 to 100. So we start at 0 and go to 100 in steps of 2. And we might take the odd numbers from, say, 1 to 75. So we don't have the same length here, right? So the length of A is 50. The length of B is 37. And A has, it's in ascending order, 0 to 98 in steps of 2. B is 1 to 73 in steps of 1, in steps of 2 again. So now if we say merge AB, then we get something which actually returns this merge list. Notice that up to 73, which is the last element in B, we get all the numbers. And then from here, we get only the even numbers because we are only copying from A, right? And if you want to check the length of the merged list, then it is correctly 37 plus 50 is 87. So if we go back and look at this code again, then it appears as though we have duplicated the code in a couple of places. So we have two situations, case 1 and case 4, where we are appending the element from B into C and we're incrementing J. And similarly, we have two different situations, case 2 and case 3, where we are appending the element from A into C and appending and then incrementing I. So it is tempting to argue that we would have a more compact version of this algorithm if we combine these cases. So if we combine these cases, then we can combine case 1 and 4. So remember, 1 and 4 are the ones where we take the value from B. So we combine 1 and 4 and say either if A is empty Or if B has a smaller value, then you take the value from B and append it to C and say j equal to j plus 1. On the other hand, either if B is empty or A has a smaller value, then you take the value from A and append the index in I. Right? So let's see what happens if we try to run this code. So here we have a file merge wrong.py. The name suggests that there's going to be a problem where we have combined case 1 and 4 where we append the element from B into C, and 2 and 3 where we combine the element, append the element from A into C. So let's run this and see. So now we take merge wrong as our starting point. And let's just do a simple case. So supposing we take A as 2, 4, 6 and B as 1, 3, 5, then we would expect 1, 2, 3, 4, 5, 6. So let's try to merge A and B, right? And now we get an error which says that we have a list index out of range. So a list index out of range suggests that we are trying to access some element which is not present. And it so happens that this isn't the case if I equal to M or AI equal to BJ, greater than BJ. So let us see if we can diagnose what's going on. So one simple way of diagnosing what's going on is to just insert some statements to print out the values of the names at some appropriate point. Now here, since we are having an error inside the while loop, what we have done is we have added this statement print, which, as I said, we have not formally seen. We will see it in the next week, but it does the intuitive thing. It takes the names M, N, I, and J and prints them out in that sequence on the screen so that we can see what's happening. So let's now run this again. So we run the interpreter, load this updated version of merge wrong, set up A and B as before. So A is 2, 4, 6, B is 1, 3, 5, and now we run merge, and now we see what's happening. So M and N are the initial lengths, 3 and 3, and these are the values 0 and 0 are I and J, the pointers. So J becomes 1, then I becomes 1, and so on. So at this point, this is where the problem is, right? So what we have found is that if I is equal to M or AI greater than BJ, so I is not equal to M, right? So I is not yet 3. So then it is trying to check whether AI is bigger than BJ, but at this point, unfortunately, J is N. So if we had these cases in order, we would have first checked if I is 3, then if J is 3, and only if neither of them are 3 would we have tried to compare them. Whereas now we are only checking if I is 3. Since I is not 3, we are going ahead and checking the value of AI against BJ. But unfortunately, J has become 3 already and we have not checked it yet. So by combining those two cases, we have allowed a situation where we are trying to compare AI and BJ, where one of them is a valid index and the other is not a valid index. So although it looks tempting to combine these two cases, one has to be careful when doing so, especially when we have these boundary conditions. When we are indexing lists, we must make sure that the index we are trying to get to is a valid index. And sometimes it is implicit and sometimes we have to be careful. And this is one of those cases where you have to be careful and not optimize these things. Otherwise, you have to have a separate condition saying if I is equal to M or J is less than N, and which becomes more complicated than the version we had with 4 explicit cases. So you may as well go back to the version with 4 explicit cases. So now that we have seen how to merge the lists, let's sort them. So what we want to do is take a list of elements A and sort it into an output list B. So if N is 1 or 0 actually, so if it is empty or it has got length 1, we have nothing to do. Otherwise, we will sort the first half into a new list L, and sort the second half into a new list R, L for left and R for right, and then we will apply the earlier merge function to obtain the output list B. So this is a very simple function, except that we are going to be sorting different segments or slices of our list. So we will actually have merge sort with an input list and the left and right endpoints of the slice to be sorted. So if the slice is a slice of length 1 or 0, then we just return the slice as it is. So it's important that we have to return that part of the slice and not the entire part of A, because we're only sorting. So remember when we broke up something into 2 parts, for example, right? So then at this point, we have to return the sorted version of this slice, not the entire slice. So we have to return A from left to right if it's a base case. Otherwise, we find the midpoint. Then we recursively sort the portion from the left-hand side of the current slice to the midpoint and put it in L. Then we take the midpoint to the right, put it in R. And we use our earlier function merge to get a sorted list out of these two parts, L and R, and return this. And so this is a very straightforward implementation. There are no tricks or pitfalls here. The only thing to remember is that we have to augment our merge sort function with these two things, the left point and the right point. We had a similar thing, if you remember, for binary search, where we recursively kept halving the interval to search. So we had to keep telling it in which interval we are searching. So let's look at a Python implementation of merge sort. So here we have a file merge sort.py. We start with the function merge, which we saw before, with the four-way case split in order to shift elements from A and B to C. And then we add at the bottom of the file the new function merge sort, which we saw in the previous slide, which takes a slice of A from left to right and sorts it. If it's a trivial slice, it returns the slice as it is. Otherwise, it breaks it into two parts and recursively sorts them. So let's see how this would actually run. So we take Python and we say from merge sort import all the functions. And now let's take a larger range. So supposing we take all the odd numbers followed by all the even numbers. So we say range 1 to 100 in steps of 2. So those are the odd numbers. And then all the even numbers in the same range, say. So A has now odd numbers followed by even numbers. So you would imagine that if I sort this from 0 to the length of A, then you get the numbers sorted in sequence. Now, what if I take a larger list, 1000, right? Then I get again the thing sorted. Now our claim is that this is an order n log n algorithm, so it should work well for even bigger lists. So if I say 10,000, which remember would take a very long time with insertion sort or selection sort. Okay. Question is how long it takes here, and it comes out quite fast. We can go further and say 100,000, for example. And even here it comes reasonably fast. So we can see that we have really greatly expanded the range of lists that we can sort by moving to an n log n algorithm, because now merge sort can handle things which are 100 times larger, 100,000 as opposed to a few thousand, than insertion sort or selection sort. Another small point to keep in mind is notice that we didn't run into this recursion limit problem that we had with the insertion sort, which we defined recursively. So there, for each element in the list, we were making a recursive call. So if we had 1,000 elements, we were making 1,000 recursive calls, and then we had to increase the limit. Now here, even for 100,000, we don't have the problem. And the reason is that the recursive calls here are not one per element, but one per half the list. So we're only making log n recursive calls. So 100,000 elements also requires only log 100,000. Remember, a log 1,000 is about 10. So we are making less than 20 recursive calls. So we don't have a problem with the recursion limit. We don't have any pending recursions of that depth in this function. So we have seen merge sort in action, and we have claimed without any argument that is actually order n log n, and demonstrated that it works for inputs of size 100,000. In the next lecture, we will actually calculate why merge sort is order n log n.